Hello everyone, we are the second group from the Star Rocket team. Today, I would like to introduce our water rocket design, simulation, and testing results. Our target requirements are mainly divided into 4 major items, the first being achieve a straight line distance of 17 to 20 meters. The second item is that our rocket shape must be streamlined to reduce drag. The third item is that our center of pressure, CP, needs to be behind the center of gravity, CG. The fourth item is that we need to create 3 relation diagrams, which show the impact of pressure on water volume regarding flight distance, plotting speed and acceleration versus time, as well as the effects of water volume and pressure on nozzle exit speed. The entire timeline is mainly divided into early stage requirement definitions, design discussions, and finally, the later stages involve finalizing the design, simulation, and producing and testing the prototype. In terms of budget, we spent approximately $700, which includes 3D printing PLA materials, adhesives, and the bottle body. In rocket design, we first used OpenRocket to sketch the preliminary shape of the rocket and define an available bottle diameter. We calculated the estimated length and net weight of the rocket, enabling the software to compute stability, CG, and CP according to design requirements. The left image shows a 3D model from OpenRocket, where the blue point represents the center of gravity, CG, and the red point represents the center of pressure, CP. The right image shows the actual prototype placed on the launch pad for the competition. For the nose cone, we adopted a conical design, using a sharper shape that matches the diameter of the rocket body to increase flight stability. Additionally, a thicker design in 3D printing can move the rocket's center of gravity forward, increasing stability and durability. For the tail fins, we adopted a trapezoidal base design and then used OpenRocket's customization feature to elongate and deform it. According to NASA data, we chose to arrange the tail fins in a ring with 3 pieces spaced 120 degrees apart. For simulation, we used 3 methods for cross-comparison, the first being the water rocket simulator provided by NASA. The second type is an online thrust simulator, hoping to estimate total thrust and create parameter charts. The third method utilizes the built-in flight simulator of the OpenRocket software. In the NASA simulator, we can adjust the parameters of the nose cone, payload, rocket body, and tail fins ourselves, displaying the results visually. In the left image, we see the interface for defining the nose cone, with the material approximating PLA using plastic. The right image shows the definition of the tail fins, and we have done our best to reduce the drag coefficient. The following left image shows the final rocket body and output thrust into the parameters of the simulator shown on the right. Setting the launch angle to 20 degrees, with no crosswind and at sea level, the simulation results in the following video were obtained. The launch results showed that the rocket landed 1.04 seconds after launch, with a horizontal distance of 18 meters. For the thrust simulator, its main feature is the ability to fine-tune more parameters, even including the shape of the plastic bottle. Initially, we hoped to obtain the thrust curve by adjusting more parameters, importing into OpenRocket's simulator. However, due to incompatible data formats and lack of a source code, we had to abandon that option. However, we can still determine the class of engine. We can also obtain the required speed, acceleration, height, and thrust versus time plots for the competition requirements. To verify the accuracy of our thrust estimation once more, other simulator can even account for the length of the intake pipe, bringing it closer to our competition requirements. After comparison and verification through various charts, including internal air pressure and nozzle exit speed, we confirmed that the total thrust of this water rocket is around 8 to 9 N. Considering that the wind in Hsinchu is quite strong, we set the simulated rocket engine to 9N, Class C. We also set the launch site at the latitude and longitude of the Tsinghua University lawn, with the launch angle set to 20 degrees. The results indicated that in calm conditions, it could still achieve 18 m, but when accounting for actual wind speed, it could only reach 8 m. Next, the above shows the parameters we actually launched with. Due to the disastrous results, we adjusted the launch angle to 30 and 45 degrees for testing. Thus, we witnessed the tragic moment of Professor, the wind on the lawn is really strong. In conclusion, the wind in Hsinchu is like an invisible wall, also due to a leakage problem of the launch pad. In the future, we will add structural rings, with 3 slots to fix the fins to ensure the stability and flight direction. Finally, let's have some lighthearted and passionate, behind-the-scenes moments.
哎，成功不要输啊！不要，你心都不要有的，不要丢脸。